All right, for the following question here, they give us a challenging polynomial to solve for here. They want us to find when this is true. Typically, when you go to solve for this, you expand everything out, bring everything to one side, and try to apply your factoring techniques. We're going to go ahead and do that, see why that does fail, and show you an alternative solution sort of when you get into that situation. So starting us off here, let's go ahead and expand and bring everything to one side. Doing so, we get the following. So now I have a degree 4 polynomial, and I want to go ahead and apply some of my factoring techniques. You'll see here sum or difference of cubes, difference of squares, GCF. None of that works here. Factor by grouping also does not work. So in this case here, our next step would be the rational root test. Using the rational root test, you have the following rational roots to examine. So using the rational root test here, the only two rational roots, if this polynomial does have a rational root, it's either plus or minus 1. Let's check these using synthetic division. So now in this situation here, I went ahead and checked plus or minus 1, and by the rational root test, none of these had worked. None of these were roots. So the conclusion is therefore this polynomial, if it does have any real roots, those real roots must be irrational. Let's take a look at now at a alternative technique in this situation, because at this point there's nothing more we can do. We've used our factoring techniques, none of those worked. We tried the rational root test, none of those worked. So now I know this polynomial, back to the decomposition of it, either this has 4 complex roots, 2 real roots, and 2 complex roots, or it has 4 real roots. And now we know that if that is the case, those real roots are all irrational, and these 2 real roots will also be irrational. So let's take a look at an alternative technique we can try now. Okay, so now we're in a situation where we have our degree 4 polynomial. We haven't been able to find a GCF, difference of squares, sum or difference of cubes, group factor by grouping. We tried the rational root test, none of that worked. So how do we factor this? How do we break this down more? The observation here is that first I can break this up into the product of 2 quadratics. This will be ax squared plus bx plus c. Again, I don't know what that quadratic is going to be. It could yield complex roots, real roots, or a mix of the both. Times another quadratic, we'll call this dx squared plus ex plus f. But what I do know is that when I expand out this quadratic here, the coefficients of these quadratics both have to be the same. Therefore, that'll generate some equations and hopefully allow us to solve for our a, b, c, d, e, and f variables. And then once we do that, we have quadratics, and we can go ahead and use the quadratic equation and get these roots. So let's expand out this expression here and get the following quadratic. Expanding, we get. So expanding out here, we get the following. And now again, these 2 quadratics must be equal because I know that this will factor. Now the next observation here is we have more variables than equations. So this is an overdetermined system. You'll notice here we have the variables a to f, which is going to give us 6 variables, but we only have here, if you count your equations, we're going to be equating each coefficient. So in this case, we're going to let AD equal 1, we'll let BD plus AE equal -5, et cetera, et cetera. It's only going to generate us 1, 2, 3, 4, 5 equations. So we can let some variables, we can define them to be anything we want. The idea here is our first equation is AD equals 1. A is represented by your coefficient here. Again, I'm going to go ahead and let A equal 1, and therefore that implies that D must equal 1 because I'm allowed to introduce a value for one of these variables. So now we have A is 1, and therefore D is 1. And similarly here, I'm going to go ahead and I'm going to let C equal 1, and therefore we can conclude that F is going to equal -1. Now going ahead and going back to our equation here, I'm going to substitute these values that we found here for A, D, C, and F, and it'll simplify this equation a bit. Taking a look, we get the following. And again, letting those values be 1 and -1 as we had defined, I get the following sort of reduction in this polynomial. So now I can equate these coefficients. I know that B plus E is going to equal -5. I know that BE is going to equal 6. I know that E minus B is going to equal +1. And now we can go ahead and solve these. So we have an overdetermined system here. If I want to solve this, I can make the observation that if I take equation 1 and add it to equation 3, I'll end up canceling off my B values. Adding equation 1 and 3 together, I end up getting here 2E is equal to -4, so E is -2. And therefore, I can go ahead and solve for B. Subbing into equation 2, for instance, I know B times E is supposed to be 6. So b times negative 2 is 6. So my b value is negative 3. So now I've got e is negative 2, and b is minus 3. And now we can go ahead and we actually found our two quadratics here. Let's take a look at how this degree 4 polynomial breaks up. Going back to our degree 4 polynomial, I now know that this will break up into x squared minus 2x minus 1 times x squared minus 3x plus 1. And again, that's by the values of a, b, c, d, e, and f that we found. We already know that we're not going to get irrational roots on these, so using the quadratic equation, we have the following roots. Therefore, the following polynomial here is going to equal 0 at 1 plus or minus root 2 and 3 plus or minus root 5 over 2. Thank you.